Alrighty, ladies and gentlemen. I'm going to roll through the answers for homework A, B, and C for this unit. Um, try to give you some pointers on figuring out what's what as we go over these things. So, in number one, we're supposed to identify the type of intermolecular forces present as if these were all solids. And so let's make this clear. We have a solid argon, 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 or we have a solid hydrochloric acid, hydrochloric acid, hydrochloric acid, or we have solid CH4, CH4. It's that compound repeated a million of times, and what's holding it together. So argon is nonpolar, and a nonpolar atom, so it just have to be London dispersion forces. Hydrochloric acid is a individual molecule, and when you draw it, it's definitely polar, so it's going to have strongest force is going to be dipole-dipole, and then weaker is going to be London dispersion forces. With molecules, you always have London dispersion forces. Those are always hiding in the background if they're not the primary. HF, well, hydrogen and fluorine have a very unequal relationship, so that's going to be extremely polar, called the hydrogen bond. Hydrogen bonds also are called dipoles, and then it's got, of course, London dispersion. Calcium chloride, you have a cation and an anion, so that's held by ionic bonding. CH4 is nonpolar, so it's going to have London dispersion forces. CO, you might actually need to draw this one. It's C triple bonded to O, and you have to move some electrons around. It's definitely a dipole, so it's also going to have London dispersion forces. And then NaNO3 is an ionic compound. You have the sodium and the nitrate. All right. Predict which substance in the following pairs should have the greater intermolecular forces. So we ranked intermolecular forces, and the three primary London dispersion forces, dipole-dipole, and hydrogen bonding, in that order. London dispersion force is the weakest, then dipole-dipole, and then the strongest of the three primary ones is hydrogen bonding. So A, you have CO2 and OCS. CO2 is nonpolar, OCS is polar, so it would be stronger because dipoles have stronger intermolecular forces. Also, you have to factor in the mass. OCS has a slightly higher mass. SeO2 versus SO2. SeO2 and SO2 are both polar, but selenium is a larger atom than sulfur, so there's more electrons. So not only is it more polar, but with more electrons and more energy levels, it's also more polarizable. So SeO2 would probably have stronger bonding between it. In C, we have two molecules that are hydrocarbons with nitrogen on the end attached to some hydrogen. So with that nitrogen on the end, they're going to be able to do hydrogen bonding. The first molecule only has one nitrogen on one end, and the other molecule has nitrogens on both ends of it. So the second molecule can do more hydrogen bonding, and therefore it's going to be more attracted to its nearby molecules and have stronger forces. In D, we have ethane, which is nonpolar, and we have what's H2CO? That's formaldehyde, which is very polar. So formaldehyde, the H2CO, would have stronger dipole-dipole interactions. All right, and we draw the next one, CH3OH versus H2CO3. Both are polar, but CH3OH, the OH is going to allow for hydrogen bonding. All right, and they often try to hint at the way it's supposed to be put together. Number 3, let's rationalize these boiling points. Remember, boiling points, that's how hard it is. That's a measure of the temperature it takes to break these molecules apart. The higher the temperature, the harder it is to break it apart. I'm going to repeat that. Boiling point is a measure of how hard it is to break these molecules apart. If that temperature is higher, it's harder to break it apart. So both these molecules are hydrocarbons. There's 5 carbons, 12 hydrogens, but the boiling points are different. So we're asked to explain why the boiling points are different. They're both nonpolar, so we got to ignore that. They both have the same basic formula at molar mass. That's not a help. So it must be the shape of the molecules. The linear shape of the N-pentane allows for the electrons to be shifted a long distance away from their home. That shifting is called It's saying it's polarized. Whereas with the other one, there's not a large distance the electrons can travel, and they would shift back a lot sooner. In the B, we have HF versus HCl. HF obviously has a much higher boiling point. It's 105 degrees higher, which means its bonding must be stronger, and HF would have hydrogen bonding. In C, we have HCl versus lithium chloride. Lithium chloride has ionic, far stronger attractions and ionic bonding because it would be strong coulombic forces. And then we have N-pentane versus N-hexane. So both of them are these straight line chugga 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 and chugga 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 chugga. That's what the N means. It's just a straight line. You don't have to know that N means a straight line. Not yet. Wait till you get to organic chemistry for that. Notice how they've given the name and the formula. So N-hexane is much longer, and therefore its electrons can be spread out along a farther, polarized across a longer distance, and that long distance is also a factor, is more contact area for the electrons to interact. Number 4. Which one would have the highest boiling point? So they're not telling us the boiling point. We have to come up with some reasoning. So Cl2 is nonpolar, krypton is a nonpolar atom, and HBr is a polar molecule. Well, it's a polar molecule. It should have the highest boiling point. I also want to point out that they've picked 3 pieces that are about the same mass. HBr is about 80, chromium is about 80, and chlorine is about 70. So the masses are not radically different. They're all pretty big masses, but HBr is polar. Which one would have the highest freezing point? Pretty much the same question. You're still trying to break it apart. NaCl would probably have the highest freezing point, meaning, Let's realize that freezing point is actually synonymous with melting point, but it's just from a different perspective. I'm standing on one side of the line and you're standing on the other side of the line, but it's still a line. So the freezing point and the melting point is the same value. It's just which side of the line are you on. So if you want to say which one has the highest freezing point versus which one has the highest melting point, you're asking for the same point. I would prefer to think of it as melting, honestly. Which one would be the hardest to melt, the harder to break down from a solid to a liquid? And NaCl should be the hardest of these 3 because it's ionic. I always like to make sure you really understand what these terms mean, though. Which one has the lowest vapor pressure? What the heck is vapor pressure? Vapor pressure is the molecules that are turning into a gas and adding to the pressure around the solution or solid or whatever. So which one would give off the most gas or the least gas? So we're looking for the lowest vapor pressure, so we're looking for the least gas, meaning it's going to say it's a liquid or a solid. Cl2, Br2, and I2 are all nonpolar, but their masses are different. I2 has the most number of electrons, and it's got the largest mass, so it's not going to be vaporizing nearly as easily as the other 2. Which one would have the lowest freezing point? Well, this one's kind of different. Which one would freeze or melt at the lowest value? So you have all 3 of these as a solid or a liquid. Which one's going to be the lowest? Well, it's going to be the thing that has the weakest forces. The lower that freezing point is, the harder it is to get it to freeze because its forces are very weak. So CO2 and N2 are both nonpolar, but N2 is nonpolar and a very small molecule. It's going to have very weak forces, so it's going to be hard to freeze it, meaning the temperature is going to have to be extra cold. Which one has the lowest boiling point of these? Kind of the same conversation. All 3 of them are nonpolar. CH4 is the smallest molecule, and it's going to be the hardest to get to boil. That's not what I meant to say. It's going to be the easiest to get to boil. Because it's the smallest, it's going to be the easiest to turn into a gas. This one's bigger. It's going to be harder to turn into gas because it's going to have stronger forces. This one's the biggest of these 3, so it's going to have the strongest forces of these 3. So you would expect to see, this is propane. Propane is going to have to be warmed up more to reach the boiling point than methane. That's methane. Which one would have the highest boiling point? Which one would be the hardest to break apart? So higher boiling point, hard to break apart. low boiling point, easiest to break apart. So HF would be the hardest to break apart of those because it would have hydrogen bonding. All right, we've switched to worksheet 2. Yay, worksheet B, I guess it's called the right thing. Um, Now we're talking about what type of solid are we dealing with and things like that. So B2H6, that's one molecule. You should draw the Lewis dot structure just to make sure you realize it's one molecule. Would it conduct electricity as a solid? No, because it's a molecular solid. Um, and molecular solids don't conduct electricity very well. There's no free moving electrons or ions. Probably a gas, and it would be held together by molecular forces, in this case, London dispersion forces. SiO2 was on the short list of network solids we talked about. I had to make the recommendation of just memorize the couple of network solids. There's no nice way to kind of remember the couple. CSI is crime scene investigators, but it's also an ionic compound, and tungsten's a metal. All right, moving down here. Number 5, consider the two different organic compounds. Here's the formulas and discuss their conditions. Which one would be a liquid, which one would be a gas? This one's more likely to be a liquid, this one's more likely to be a gas. Why? The O has the hydrogen on it. That is a recipe for potential hydrogen bonding. If the hydrogen is connected to oxygen, nitrogen, or fluorine, then there can be hydrogen bonding between this molecule and its brother and sister twins that look like it. So it's going to have stronger bonding and more likely to be a solid or liquid. This one's going to be bent and polar because of the oxygen, but it doesn't have hydrogen bonding because there's no hydrogen attached to the oxygen. And a whole bunch of what type of solid would form. CO2 is a molecule, so it's going to have molecular intermolecular forces. Since it's nonpolar, it would have London dispersion forces. We already mentioned SiO2 is one of the networks. Silicone is also one of the networks. CH4 would be one complete molecule, nonpolar, ergo London dispersion forces. Ruthenium is a metal, so it would be a metallic solid. Iodine is a molecule, so it would be a molecular solid held together by London dispersion forces because it's nonpolar. KBr, that's ionic. H2O, that's a molecule, but this molecule is a lot stronger than the others because it's got hydrogen bonding. Hydrogen bonding and dipole-dipole and London dispersion forces. It's got all three. All right. Remember, with molecules, you always have London dispersion forces, and you might have dipole-dipole. And if you have HO or F, NO or F, you might also have hydrogen bonding. NaOH is ionic. Uranium's a metal. Calcium carbonate's ionic. Ph3. I guess Ph3. Ph3 would be a molecule because that is one complete unit, and it'd be held together by dipole-dipole and London dispersion. Why is that one not hydrogen bonding? Because it is not one of the NO or F molecules. Cool?